pleased to welcome Dr. Veerabhadrappa ST, Associate Professor, Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Bangalore. Today is here to give a talk on operational amplifier circuits and its application.
We start with operational amplifier circuits and what do you mean by an op-amp or operational amplifier? What do you mean by an op-amp? Actually, initially operational amplifier was developed in 1954 using vacuum tubes. Now we are using a semiconductor diodes and devices. Earlier, before invention of the, immediately after the invention of the diodes and transistors, the first operational amplifier is developed in using a vacuum tubes. Even today, that vacuum tubes and vacuum diodes are used in defense for operating on very high frequency amplifiers and generators. Even in FM stations also there people are using vacuum because that will use a clear signal and generation of the signals. Now, why it is called operational amplifier? The next question arises. Before invention of a digital computer, most of the computations were done using an operational amplifiers. Operational amplifier is a linear integrated circuits which consisting of a differential amplifier, I gain, which can be used for all arithmetic operations like addition, multiplication, subtraction, and differential operators. Along with that, even we know that integrator and differentiator are also known as a linear operators. I hope these things you study in your signals. You study now linearity property, you verify that any signal is to be a differential operator and integrator operators are also a linear operators, isn't it? Means, based on that one only we can do many mathematical operations in your signals or any subject. You are not dealing with a non-linear signal. Therefore, you can say that a differential means basically that operational amplifier consisting of that four stages: a input stage, a gain stage, level shifter and output stage. That first two stages, that input stage, a differential means in the first stage which is consisting of a dual input, a dual output. Therefore, that first stage is to be known as a balanced differential amplifier. Because of that reason, that the gain of the input stage is always very high. One thing, and second thing is that input impedance is also very high. Is followed with a unbalanced differential amplifier, means a dual input and a single output. Okay. When dual input and single output means that is output is a single. Next one is to be used for a level shifter because you have to balance that signal. Finally, that output stage which is normally used as a buffer. In most of the cases they use a push-pull class B amplifier, typically used in the output stage, or sometimes they use a source followers or the emitter followers. Because to maintain that output impedance is to be as low as possible. Because of that reason, that the input stage is a differential amplifier with very high gain, output stage is a push-pull amplifier, or a simple one is a common source or common emitter amplifiers. I hope you are heard of these things. Then, if you consider a dual input means the package which consisting of if you consider the MUS741, normally what you are used in your laboratory sessions, which consisting of 8 pin, which consisting of that two inputs are V1 and V2 are nothing but an inverting input and a non-inverting input terminals. Inverting input means that output is a 180-degree phase shift of the input. Therefore, that input terminal is known as a inverting terminal or input terminal. Therefore, V0 is equal to minus of V1. Similarly, a non-inverting terminal means that output is follows the input signal. A phase shift of 0 or 360 degrees. And then we have the two power supplies, power supply V minus and V plus for pin number 7 and 4. And output is to be taken across pin number 6. And first two stages, 1 and 5 are used for offset null. Okay, and pin number 8 is not connected. What do you mean by offset and null? Okay, for this ideal operational model, we have to consider that gain is an infinite. because that open loop gain of that operational amplifier is infinity, and input resistance is also an infinity because of the differential input, and output resistance is 0 ideally. Practically we have that about 75 ohms for MUS741, and input resistance is to be about 2 mega ohms, and gain is to be 2 into 10 to the power of 5, and input voltage is 0, and input current is also 0, I plus and I minus. I plus indicating a non-terminal current flowing to the non-inverting terminal, and I minus is the current flowing to the inverting terminal. Apart from that, you studied, I hope you heard about the offset, input offset voltage, input output offset voltage. What it means?
To bring the
No, what do you mean by offset voltage? Input and output offset voltage.
so without even sending an input to the
Means even if the two terminals are grounded, inverting and non-inverting terminals are grounded, due to the biasing, okay, means normally that differential amplifier may be constructed by using a MOSFET or the transistors. Due to the biasing, some voltage to be present. There is nothing but the input offset voltage across the terminals. And also, even in the these two are grounded, it gives some output voltage. That is nothing but the output offset voltage. To nullify that output offset voltage, to reduce the error, then many circuits are existing. A simplest way is you have to adjust that, using a potentiometer, you have to adjust that output voltage equal to 0 by connecting between the 1 and 5. Or you can also use an external circuit. That is about the ideal operational model. Now, if you are consider that operational amplifier, V1 and V2 is an V1 is the input applied to the inverting terminal, and V2 is to apply to the non-inverting terminal. Means internally that consisting of, because of that differential mode, there is a constant voltage source followed with some resistance, a Thevenin's equivalent model. Okay, that voltage is nothing but the constant voltage source what you have specified inside is equal to a gain A into open loop gain A into the differential input voltage existing between the non-inverting terminal and the inverting terminal, that is V2 minus V1. Then that is the output is to be taken, this is a open loop gain, a open circuited gain, that is V0 is equal to AOD, that is a differential. Some books they use AID, that is open loop gain, followed with V2 minus V1. V2 minus V1 is to denote with VAD, a differential input voltage. Then a small input voltage is applied. What is the output? What is the expected output voltage? Because V0 is proportional to V2 minus V1. That proportionality constant is to be replaced by a voltage gain, open loop voltage gain. What is the output voltage? When a microvolt input is applied to the operational amplifier. Practical cases or ideal case. In ideal case, what is the expected output voltage? Even small input voltage is applied.
very high.
Huh? High. Means what is the expected value, approximate value? 10 to the power of 5, 6. Is it possible? Next question arises. Is it possible? Yes. According to mathematics, no doubt. V0 is equal to AID into V2 minus V1. V2 minus V1 is 1 microvolt or 10 microvolts. The gain is to be infinity. Output is infinity. Are you expecting infinite output voltage? What is the expected output voltage? Saturation. Because I hope you studied transistor characteristics and this transistor amplifier. The operating point is close to the saturation region. Means even if it is in the middle of the active region, that gain is about 100. You did any experiments of transistor amplifiers? Common emitter amplifier you did. For example, if you apply 1 volt output voltage, what is the expected output voltage? Input voltage is 1 volt. What is the expected output voltage?
You get sort of a pulse.
Definitely you are going to get a square wave. because this implies that transistor means the output goes in behind a linear region. In this case also here, that output voltage when the VID is much greater than one you have specified, means that is to not the 1 in 10 to the power of something 5 for an operational amplifier. Even a small input voltage is applied, that due to the very small linearity, then what happens? That's directly it reaches to the a plus saturation voltage, that is approximately a V saturation, that is nothing but plus VCC. And similarly, when that input is negative, V2 minus V1, because when you set V2 is equal to 0 and V1 is equal to some 2 microvolts, that input is negative. Because that is output voltage is also a negative, therefore it goes to the a negative saturation voltage. As we clearly specified in the reasons of operation, this is a negative saturation, this is a positive saturation. In a linear region means output follows the input signal. That region is to be very small in case of the open loop voltage gain. How do you increase the linearity of the amplifier? Next question arises. How do you increase the linearity of the amplifier?
Feedback.
Due to we have to give a feedback. What is the amount of feedback? That question arises once again. Means that feedback is nothing but a partial of the output signal is to be fed back to the input. Normally, you have to consider two types. One is a negative feedback amplifier, other one is a positive feedback amplifiers. A positive feedback amplifiers are used for the generation of the waveforms, either sinusoidal or a non-sinusoidal waveforms. A negative feedback amplifiers are used to increase the linearity of the amplifier. Means that means then when what it means a linearity of the amplifier increases? Means that output voltage not only depends on your open loop gain, that mainly controlled output voltage will be controlled through that external components, isn't it? Means instead of simply that the AOD is to be changed, we can set according to your wish. Therefore, a negative feedback is introducing that negative. One is linearity is increases, then is stability of an amplifier increases, distortion reduces, input impedance is also increased. That depends on types. I hope already you studied those things, 4 types. In series amplifiers, feedback amplifiers, input impedance is increases, output impedance is further decreases. And in vice versa in case of shunt amplifiers. In shunt amplifiers, input impedance is decreases, output impedance is increases. You have done 2 experiments, no? That is the transistor amplifiers. If you remove a capacitance between across that RE, see what happens to the amplifier. I hope you studied a common source amplifier with feedback, with source resistance and without source resistance. What is the effect? Sensitivity increases. What it does?
It takes in noise of the amplifier.
Not noise. Stability increases or sensitivity increases means definitely noise reduces. Ultimately, when you remove that CS for a common source amplifier, I hope you have MOSFET only in the module 2, isn't it? What happens to that? You have to go back and recollect that amplifier gain. What is AV without source resistance RS, if it is possible? AV is equal to minus GM into RD is in parallel with RL, or simply minus GM into RD, isn't it? When that source resistance is introduced, means the drain current is to be, that is nothing but a current series feedback. Means the drop across the source resistance RS is fed back to the input. Due to that reason, a gain of the amplifier is reduced. That AV is equal to minus GM RD divided by 1 plus GM into RS. Then one of the major difference between that a common source amplifier with source resistance and without source resistance. Okay, means that is nothing but a feedback. I'm introducing that feedback. Means that nothing but a negative feedback is introduced. As a negative, due to the negative feedback, what happens is this linearity region is increased. As a result, even you can apply some few volts. Based on that, your a gain of the amplifier. Isn't it? Then, based on this are the output voltage characteristics. This is a very, very important concept you should remember. Whole course, module 4 and module 5 mainly depends on this one only. The entire thing is to be depends on this concepts. Next is, you have to consider the feedback amplifiers, that is a inverting amplifier. Introducing a feedback amplifier. Means that what is the output voltage of this? I hope you already studied this. What is the output voltage? How do you derive it? KVL is easier, KCL is easier.
KCL.
Throughout this course, you have to use only KCL. Easily you can addition. Means if you are, what is the voltage at this point? Why it is 0?
Virtual shock.
Virtual?
Virtual ground.
Virtual. Means you have to consider this is a current I1. Means applying KCL because this is a node A. So applying KCL at this node A, then you are going to get I1 plus IF, because incoming currents are equal to the outgoing currents. This is incoming, that is outgoing. We can say that I1 is equal to IF plus II. This is a current flowing through this is nothing but II. What is II? 0 ampere. Why it is 0? Because that I input impedance. There is no current is to be flowing through this resistance. Because whatever the current, therefore II is approximately equal to. Then use this notation, means incoming current means you are showing that this is an incoming current, this is an outgoing current. Therefore you can write a V in minus VA equal to VA minus V0. Isn't it? Therefore you are going to get this expression is nothing but a V in minus VA. You are going to get that AV is equal to minus RF by. Okay. Means you have to use this relation, that is a V in minus VA, VA minus V0 by RF by RF, then you are going to get this value. Now, actually you have to use a compensation circuits. In a compensation network, how you are going to do? There is a potentiometer is connecting between a pin number 1 and pin number 5. Then you have to, that potentiometer third terminal is connecting to the a plus or minus VCC. Means you have to, by adjusting the value of the resistance, you have to nullify the output offset voltage. Okay, that circuit is missing. Now, similarly, a non-inverting amplifier. A non-inverting amplifier, that input is applied to the non-inverting terminal, and that circuit is to remain same. There is no change in the circuit. Then you have to replace source and the ground, isn't it? And compared to the how to remember that things is, you have to remember that circuit is to remain same. There is no change in the inverting amplifier and the non-inverting amplifier circuit. What is the change? Re-interchange that source and the ground. Means source is connecting to the a non-inverting terminal, and other end of the resistance is to be connecting to the grounded. Then what is the gain? What is the expected gain?
1 plus RF by R.
1 plus RF by RI or R1, whatever it may be. Therefore, output voltage is equal to. Then what is the role of that RL here? Is it effect on the gain? What is the amount of current flowing through that load resistance RL when compared to I0? You are written IL. What is the current, expected current flowing through this? I0 plus? It means whatever the current flowing through that resistance, because you are going to get this is the V0 value, then this is grounded. That current is to be nothing but sum of this, because you have taken this direction, that is IF. This because you are taking that. Why this is to be I naught is equal to IF. Therefore, we are writing these two currents are leaving. That I naught is incoming current. That is almost that, because this resistance is 100 kilo ohms and this is 10 kilo ohms resistance. Therefore, that current is to be almost I naught is approximately equal to IF only. That a little bit current is flowing to the load. Therefore, V naught is equal to 1 plus RF by R1. Now, similarly, you would use this one is to be used as differential amplifiers. Differential amplifiers are normally used for to find the subtraction or the difference between the two signals. What is the output voltage? How do you derive it? How do you derive this condition? What is the advantage once again in a differential amplifier? Because here we are assuming that R1 is equal to R2 and RF is equal to RF. These two are equal. If they are not equal, then you have to find. First thing you have to find the drop across this point B, non-internal. Means V plus. What is V plus? V plus is nothing but a voltage drop appears at the non-inverting terminal, that is equal to, that is nothing but a drop across this resistance RF. Therefore, you are going to get this is RF divided by R1 plus RF into isn't it? Then if these two resistances are equal, then you are using a different answers. Now, what is the, we are applying KCL at this node, non-inverting terminal. That is nothing but a V2 minus V minus divided by R1 equal to V minus minus V naught by R. What is V minus? V minus is nothing but V plus because of virtual ground. Therefore, you are going to get this is nothing but V naught is equal to V2 by R1, then minus V2 by R1 plus 1 by R1 plus 1 by RF into V minus. Isn't it? Now substitute this and then simplify. You are going to get minus, sorry, this is RF, minus V2 by R1 plus R1 plus RF divided by R1 RF into V plus means V1 into RF by R1 plus. This implies that V2 is equal to minus RF by R1 into V2 minus, sorry, V1 minus V2. If the resistances are equal, then you are going to get a solution in a single step. Otherwise, that gain may be, that means if that R1 is not equal to, I will use that R2 and R3. If these two resistances are not equal, then what is the output voltage? If this resistance, one of the resistance, for example, I am assuming that this resistance is not equal to this resistance. Okay. What is our expected output voltage? What is the impact on the output voltage? Higher or lower limit? What is our impact? Means we are going to give a different weightage to the input voltage V1 and V2 if they are not equal. If they are equal, then that output is to be directly proportional to the difference of those two. difference of those two, isn't it? With a multiplied with a gain, minus RF by R1 plus RF by R1. If these two resistances are not equal, then what happens is your output voltage is equal to, I'll write like this, something A into V1 minus B into V2. Where A and B are nothing but some constant, depends on the values, means you are going to give the weightage to that. Instead of direct subtraction, you have to modify it by that factor A and then you have to subtraction these two. In some applications you are going to do that. In most of the applications you are using a simple subtraction amplifiers or a differential amplifiers. But when you are going to give the more weightage to the some signals, then you use this A V1 minus B V2. Isn't it? This is a differential amplifier by using that A. What is the advantage when you use this differential amplifier? Because of this feedback, input impedance is further increased and output impedance is further decreased. This is about the amplifiers in a DC conditions. Next is AC amplifiers. What is the difference between DC amplifiers and an AC amplifiers? What is the difference between AC amplifier and a DC amplifier? Means by what is the frequency of the DC amplifier? DC signal 0. AC signal that we can variable frequencies. Maybe anything is greater than 0 up to infinity. What is the difference between these two? If you observe from the previous circuit analysis, that output is independent of the frequency. In a DC amplifier, output is independent of the frequency. But here, in an AC amplifier, output is depends on that frequency. Means that the frequency varies, the gain of the amplifier is also varies. In some applications, that AC amplifiers are required. What is the expression for the output voltage now? Inverting and non-inverting amplifier. Okay, what is the reactance of a capacitor at DC voltage?
Very high.
It is an infinity. Means ideally it is an infinity, but practically it is not infinity. Means as the always have to say that a limit the frequency approaches to 0. What is the reactance? Reactance of a capacitor is approaches to infinity. Means is approaching, means it is very high, it is not completely open. Still there is a conductivity. Therefore always use as the limit is even if under the DC conditions that reactance is very high. What is the voltage drop across the capacitor then? Under the DC condition, what is the voltage drop across the capacitor? Because if you consider that C1 and R1 is connected in series, no? Then what is the reactance is very, where is the output voltage drop appears? Got my question or not? Yeah, that resistance C1 and R1 and capacitor C1. Reactance is very high. That where is that Vn appears? Vn appears. Okay, we will consider these two. Can you interact? This is the capacitor and C. Applying Vn. If the reactance is very high, What is the voltage drop across resistance R? Almost zero, because most of the voltage appears across the a capacitor C only. Because once again that analysis of the capacitor we are doing in a two different way. One is a transient analysis, other one is a frequency domain analysis. In a transient analysis, you are discussing about a charging and discharging. Okay, the time taken to reach that saturation region and all. But here your analysis in the frequency mode. In a frequency mode means you have to consider this reactance J XC is equal to 1 by J omega C. This is nothing but 1 by J 2 pi FC minus J XC is equal to 1 divided by J 2 pi FC. Isn't it? Means that the frequency increases. As the frequency increases, what is the voltage up across the capacitor? What is the voltage up across the capacitor? Decreases or increases? Means a frequency increases, reactance decreases, then drop across VC also decreases. Means that most of this amplifier is. Means under this condition, now you have to analyzing this inverting amplifier means this AC amplifier is to be mainly depends on that frequency. Okay, as the frequency varies, that V0 is also varies. Okay, up to what point that question arises next? To analyzing this, once I am applying a KCL at this node, A, inverting terminal. Then what is the voltage? KCL at node A. Then you are going to get VI, V in minus 0 divided by, because this is virtually grounded, directly I'll take 0, or you can write, if you want, you can write VA divided by Ri plus R1 minus J XC equal to VA minus V0 by Rf. So I am assuming that input is that I1 is input current, IF is the output current. Then VA is equal to 0. Therefore, V0 is equal to Rf divided by Ri plus R1 plus J minus JXC into VA. Directly we can rewrite. Okay. For this, what is V0 by Vi? Is the output gain. This is equal to, if you take Rf divided by Ri plus R1 is common, then you are going to 1 minus J XC divided by Ri plus. What is XC? XC is nothing but 1 by 2 pi FC. Therefore, this is equal to Rf divided by R minus Rf by Ri plus R1 into 1 minus J divided by 2 pi FC Ri. Then what is the magnitude? Because this is the case where minus Rf by Ri plus R1, where Ri is nothing but a resistance of a signal generator. I have also shown in the R0. What is R0? R0 is nothing but a resistance of the signal generator, output resistance of the signal generator. Some books they use R signal, or sometimes they use R0, or sometimes your Ri. Then Ri is to be, what is the resistance, output resistance of a signal generator? Are you used signal generators and the CROs in your laboratory? Are you observed that what is the given on the output terminal? What is that? When you are connecting a probe, no? The specifications are given. No? Are you observed? Yes or no? If you are not observed, what is that? Both the signal generator and CROs. Huh? Not CROs are only at the knob position, not CRO connecting, no? CRO probe connections. Signal generator. No. they're given something is to be given the output resistance of a signal generator. Means that impedance matching, you should use a proper probe. Okay. That resistance is to be about 60 ohms in case of a signal generator. And the CRO, it is varies from 60 to 600 ohms. If you are not observed, when you go to the lab, you have to check it. Means that is the output resistance of the a signal generator, that is nothing but the RI or R0. That is negligibly small when compared to the R1. Therefore, you can neglect it. Then this, the magnitude is, this is, therefore you can call this is gain of, because this is independent of the frequency. Minus RF by RI plus R1 is independent of the frequency. This RI is negligibly small when compared to R1. Therefore, there is nothing but minus RF by R1 is nothing but the gain of the inverting amplifier only. Gain of the inverting DC amplifier. Now, this is a component which gives a variation of that frequency. Then we define that a frequency, cutoff frequency FC is equal to 1 by 2 pi C into Ri plus. Then what is the gain now? AB. V0 by Vi. V0 by Vi is equal to, I can write, minus RF by R1. Made an assumption that R1 is, Ri is negligibly small. Then divided by 1 minus J FC by this point is clear? Now what is the magnitude? What is the magnitude of a complex number? One divided by what is square? A plus JB. What is the magnitude? Root of A square plus B square. Therefore, this is equal to a square root of 1 plus FC by F whole square. At FC, F is equal to FC 1 by root 2. That is nothing but a 3 dB cutoff frequency. That is nothing but F is equal to FC. Then that is nothing but a 3 dB cutoff frequency. Means that maintains the constant gain because of that, and then that reduces. That is one way of analysis. As the frequency increases, what happens? The reactance is decreases, a output voltage is. What is the output voltage now? Increases because that reactance. Therefore, then gain is to be almost minus RF by R. And similarly, the same thing is applicable. Therefore, RIF is nothing but what is RIF? RIF is nothing but R1 only. RIF is nothing but input resistance with feedback. First stage, R1F is nothing but the first stage. What is that? That is nothing but R1 itself. Okay. In the similarly, this is a non-inverting amplifier. For example, let's say you have to determine the resistance across R0, ROM. Already we know that why I am using that ROM. Once you have to adjust the ROM. Why you are using? Normally you are not using that resistance. That ROM, the resistance that we use the balancing purpose of the to adjust the input offset voltage and currents. Therefore, you are going to get that Vin is equal to Rin into R0. Then you are going to get the same frequency response, that is equal to FC into 2 pi FC Ri plus R1. But what is the gain? Gain of the amplifier is equal to 1 plus RF by R1. Means under the DC condition, the gain of the AC amplifier is also remains same as the DC amplifier. But only thing is that gain output voltage decreases or increases with respect to the frequency. That is about the AC amplifiers. In most of the applications, in many applications, that AC amplifiers are used. Next is a summing amplifier. What do you mean by summing amplifier? Summing amplifier is nothing but an adder. What do you mean by an adder? Addition of more than 2 or 3 signals. Here that once again we have to define into the two way. One is R1, R2, R3 and RF. This is an inverting amplifier. Summer. That output voltage V0 is equal to minus of F. Then that is R1, R2, R3 are not equal. Means that is what is that indication that you are going to give the weightage to the inputs V1, V2, V3. And then adjust the gain. If all the signals are equal, all the resistances are equal, it's not an average, it's simply an adder. When that R1, R2, R3 are not equal, then this is a summing amplifier with a different weightage. If the R1, R2, R3 are equal, then that is a simple adder with the gain. Then that R1, R2, R3 is equal, that is given by an expression, that is RF by R1, RF by R2, RF by R3. Okay. When under what condition this circuit can be used as a averaging amplifier? What is the condition required?
RF by R1 is
RF by R1 1 by 3 means that depends on the number of resistances or the number of input signals. You can set that RF is equal to N times R. If N number of input signals are 3, then nothing but RF is equal to 3 times R. Then you are going to get this resistance. R is equal to, RF is equal to RF by R1, that is equal to 1 by 3, no? Therefore, R is equal to 3 times RF. RF is equal to R by 3 or R by N. What is the difference? Where do you find this application, summing amplifiers? Simply you study this circuit. Where do you find these applications in a day-to-day life? No, forget about the you are assuming that V1, V2, V3 are signals. 3 signals. Not the voltage. For this circuit, for examination point, you say that this is V1, V2, V3 are voltages. If you are assuming that V1, V2, V3 are the signals, where do you find this application?
Audio systems.
Audio system. Next. Huh? Radio receivers. One system, not an audio system, normally in most of the musical concerts. One thing. How many instruments are connected to a system? All are having the same gain. In a musical concert, you have different instruments are there, no? You are observed how much time they took to set their instruments, tune their instruments. In your college concert, or a college function. You are eagerly waiting for 2 hours, 3 hours, no? Until they set their setup. Yes or no? That is one of the application of this summing amplifier. Not an audio system. Even audio system also, while doing that, each instruments or each signal is giving a different weightages. Because simply study this course no use. You should where exactly you are applying. This subject should be linked with your signal processing. Study now some of the signals, addition, manipulations of the signals and all. Adders and all in your signal processing. Not there in your next time. One day decision from here, sir. Definitely. Otherwise, difficult to manage. Okay. Means these are things are the same. One way. Other example is most of our signals are multimedia. For example, you have to consider a telecast of any games. What exactly you are seeing on your screen of your TV? How many signals are there? Did you check? You are in a live test match or live test or live cricket match. What are the observations on your TV screen? Video, scorecard,
and
audio. That's all. Live coverage. Next. there is a symbol of your TV channel. Which channel is broadcasting that? Means your live telecast, which is consisting, one is on video, other one is on audio, and other one image, still image. That is a logo of your telecast, and multiple text messages, not a single. One corner they are updating their live scores, India batsman score, ball wise. These are independent text messages. Means when they are telecasting of a cricket match, it can not only a single signal, it is more than 4 or 5 signals at a time. All they are processing the same gain and same frequency. Next question, what I guess. Same or different? Why it is different?
The still image doesn't have any frequencies.
Still image doesn't have any frequency. Yeah, next.
The scorecard updates every.
Text, okay, next.
The video is in microseconds.
Video in microseconds. No, you talk in terms of bandwidth. At least you already about the bandwidth. What is the bandwidth required for your telecast? Not SD, normal 4, 3 or 69. Video power. It requires more than 5 megahertz bandwidth is required. For audio, what is the audio frequency range?
50 or so, 20
How many? 20 to 20 hertz to 20 kilohertz. Maximum frequency double. Means 40 or 48 kilohertz is required. Means if you use that, for example, if you process that signals, for example, it is an ECE amplifier, it is summer, then you have a audio, video and text. Video required 5.3 megahertz. Audio required 40 kilohertz or 48 kilohertz, your MP3 you are using. And text requires it less than few hundred hertz or about 100 hertz, and even image also. Means if you process that signal, video signal with 100 hertz, are you going to get anything? You are going to get only a blank screen, even without an audio, without video. At the same time, if you process all the signals with video frequency, what is the effect? Unnecessarily you are using additional bandwidth. Then what is the data transfer rate? Huh? Because unnecessarily your battery drain out and data, because the J is giving 2 gigahertz, 2 mega, how much? Data 2 GB, that is not sufficient for you to watch one song in your YouTube. Means that is the applications of the summing amplifiers. You have to connect with that, then only you can understand in that circuits. Before invention of that digital computers and digital media, most of things are computed by using this operational amplifiers. Therefore, this is known as an operational amplifier. It is also known as an amplifier. We have one course, during my course, I studied one subject as a operational amplifier applications only. Analog computers as a subject title. You go and refer book called Analog Computers by Rajaraman. So next. I hope you understood this difference between the addition summing amplifier, adder and average amplifiers. Next. And also I told that integrator and this one is also a linear operators. Based on that assumptions only, because when you are why it is called linear, you cannot verify. In your experiments in laboratory mathematics you study, sometimes you are interchanging the order of a differentiator and integrator. Simply can do that. What is the condition required? Normally most of the mathematics teachers don't tell all these things. Simply you have to interchange that differential and integrator operator and do this, you are going to get that solution. Most of the times mathematics teachers are telling only this. I know. Why? Because it is possible if and only if you can interchange any mathematical operator if and only that operators are linear. Then only it is possible to interchange that differential and integrator operators. What is that integral operator? Because this is nothing but integration is nothing but output voltage V0 is nothing but an integral of minus 1 by C minus infinity to T R V1 by R into dt. That is nothing but, because we know that voltage across the capacitor Vc is nothing but 1 by C integral of I into dt. That what is the limits you are going to choose, that question arises. In general, they are considering minus infinity to t. Okay. Then what is I? I is nothing but current flowing through the resistance R. Therefore, you are going to get V1 by R here. One thing. Because that derivation is already you done, but not necessary at this moment. What is that required? T, minus infinity to t. Normally you have to take a break, no? At the discontinuity point. Means minus infinity to 0 until that switch off. You are assuming that always a capacitor has 0 charge. But still it is some charge, that is nothing but minus infinity to 0 and 0 to t. How long you are going to that charging. Okay. When you are applying a sinusoidal signal to this integrator, what is the expected output? What is the integral of a sine? Minus cos. Means that minus cos divided by 1 by RC. Here in this case, 1 by RC is nothing but the gain of the amplifier. 1 by RC is nothing but the gain of the amplifier or the gain of the integrator. Means that output voltage is exactly a phase shift of 90 degrees. Means whenever any sinusoidal signal is applied to the any circuit, your output is sinusoidal only. But only thing is, you can observe there is a phase shift or a phase difference because of that a capacitor C. If you apply, are you heard about the non-sinusoidal signals? Can you tell me any name? Pulse, triangle. Okay, when you apply a triangle wave to the integrator, what is the output voltage? When you are applying a square wave, pulse, what is the output? When applying a square wave, you are going to get a triangle, because integral of a constant is t. T by RC, that gain is you have to consider. Means if you are applying a square wave, to the input signal, then your output is, because of the inversion, a negative sign, minus 1 by RC gain and then decreases. Until that plus gain, that output is decreasing. When that output maintains the level of minus, then minus of minus becomes plus, then that capacitor starts, that means that signal starts increasing. T. Means that actually, instead of minus infinity to t, determine the amplitude of a signal, a square wave signal. You have to taking this direction is nothing but integrating between T1 and T2. That is output voltage. That is general conditions. When you are considering with respect to the circuit diagram or anything, you should be take the one period where that discontinuity. What do you mean by discontinuity point? In mathematics, you study discontinuity functions.
There's a break in the signal.
Breaking the signal. Normally, as an engineer, you should be thinking discontinuity point is the point at which that signal changes its state. Not breaking. Changes its state means from a square wave to triangular wave, or change level plus voltage to a minus voltage. Because here that discontinuity point is nothing but point at which that signal changing from the level a plus 1 volt to minus 1 volt. That is called discontinuity. There is no break. That is one difference between that. Means, in this case, when you are applying a triangular wave, what exactly are you going to get? The t square. T square is nothing but an example of parabola or exponential signal. And similarly, in the case of a differentiator, sinusoidal signal, differential of sine is nothing but a cos. A phase shift means there is a phase shift. And whatever the square wave is applied, triangle wave is applied. Square wave. When a square wave is applied, you did experiment or not in this? Differentiator or integrator in your laboratory? You have not done, no problem, because anyway you have not studied that signals also. What exactly you are going to get? If you are differentiating that triangle wave, square wave. 0. Isn't it? Normally when you talk about a mathematics, it is like 0. But what is the voltage at this point? Initially this is the voltage. Okay? What is the voltage at this point? 0. What is the voltage immediately after 0? What is the voltage? Some plus 1. Isn't it? What is the differentiation between these two? Means differentiation is analogous to a subtraction, integration is analogous to addition of your arithmetic. Therefore, in a differentiator, you take a V of 0 plus minus V of 0 minus. Take the difference. Means V 0 plus means immediately after 0. V 0 minus means just before 0. What is that one? 1 minus 0. Therefore, you are going to get a negative impulse. If you are differentiating not 0, means at the discontinuity point you are going to get the impulses. And similarly with respect to the T1, just before means that is a T1 plus T1 minus. This is negative, this is plus. Therefore, you are going to get T1, you are going to get plus, because minus RC by R into C by dV by dt. Means instead of 0, okay, if you apply a constant signal, definitely 0. But when you are applying a DC signal, 0. But when you are applying a square wave, you are going to get a train of impulses. Where do you occur that impulses? Impulses are occurs at discontinuity points. These are the simple applications of the normal general applications of the operational amplifier. Next is an instrumentation amplifier. Why do you need instrumentation amplifier? Next question arises. Why not it is possible to implement by using only an integrator, inverting and non-inverting amplifier? Why do you need? Most of the biomedical applications, circuits use an instrumentation amplifier. Instrumentation amplifiers are normally there are different types. That is one is in this what is the I am showing the two circuits here. This gives that instrumentation amplifier which gives the further increase the input impedance and further decrease the output impedance. Now how this circuit works? Next question arises. See that if you divide this circuit into this portion. If you draw this line, this is nothing but simple second stage. We have two stages, no? What is this stage? Last stage? A differential amplifier. What is the gain normally? R3 by R2. Isn't it? Where this is a V out is nothing but R2 by R3 with a difference of V2 minus V1. Means we have to need to find what is V1 not dash and V1 dash here, V2 dash. Because of this a negative feedback at this single stage, first stage, because we have two stages, we have the negative feedbacks at the two stages, stage 1 and stage 2. Because of these two stages, that input impedance is further increases. Output impedance is further decreases. Impedance matching. Then, what is the value of this point? How do you determine that V1 dash? Because we already have made an assumption that op amp is a linear operator, one thing. Second thing is, it obeys the principle of superposition. So, theorem is there again. Superposition. How do you solve that superposition principles? Yeah, set except one source, you have to set all the sources are equal to 0 and then you have to do this. Now, using that analysis you have to determine what is the voltage V1 dash and V2 dash. What is V1 dash? What is V1 dash? How do you solve? Means set V2 is equal to 0. Set V2 is equal to 0. What is V1 dash? When V2 is equal to 0, what is the voltage at this point? 0. Isn't it? Then what is the voltage at this point? Means we can write V1 dash minus V1 by R1, isn't it? Next is equal to this is a incoming current and also this is a current direction is with this direction, you have current direction in this direction equal leaving is equal, therefore this is equal to V1 by 0 by R gain, isn't it? Therefore what is V1 dash? V1 dash is nothing but 1 by R1 plus 1 by RG gain. Therefore, V1 dash is nothing but V1 into 1 plus R1 by, means from this amplifier, no, that is an non-inverting amplifier, one is an inverting amplifier. Therefore, you are going to get V1 dash is equal to V1 plus RF by R1. Means that is nothing but even if you consider one way of doing that, other way that at this point you are going to get my voltage, there is nothing but a voltage of across this. Similarly, when you have to set this V1 is equal to 0, then you are going to get voltage at this point is 0, then the distribution depends on these two conditions. What is the gain of this amplifier? Means you are going to get V1 dash, okay. Next is that V2 dash is equal to, V2 dash is nothing, V2 minus V2 dash by R1 equal to V2 by, R1 is equal to V2 by, V2 minus 0 by R gain. Means this V2 by V1, this gain total, if you solve this, V2 dash is equal to V1 into 1 plus R1 by RG. Okay. Finally, if you simplify this, one thing. Now we have to take the difference between these two, V2 dash minus V1 dash, that will gives that result into V out is equal to 1 plus 2 RG by R1 into R3 by R2. This circuit, maybe they use the, if you use this CS Rangan book, they use refer this circuit, 3 term operation amplifier. Alternatively, if you use that gain increases even more than that, just using a differential amplifier, using a potentiometer can vary the gain. Okay. Next is an instrumentation amplifier. What you have in your book, Gaikwad textbook. They use that is a bridge. But normally we use the bits on bits. They use this RT plus delta, that is a resistance transducer, and then RC and RB is to be used for a balancing. RA is a constant. Means here we have to connecting, this is a grounded and the source, and then these two voltages are differential input. Whatever the differential voltage appears, that is connecting to the non-inverting amplifier. What is this amplifier? First stage voltage follow. What is output is follows the input. The second stage is a differential amplifier. Even in a voltage follower also, the gain of the amplifier increases. If you recall your what is the input impedance and output impedance of a source follower? You studied source follower. Because in case of a MOSFET, no difference. All the cases because RG. Reason is gate source is always reverse biased. No? Therefore, you won't get any difference either source follower or a common drain amplifier or a common source amplifier. But in case of this transistor, the gain of the amplifier is definitely increases by beta square. Input resistance is increased by the beta. Common collector amplifiers. You don't have that in your syllabus, I think. I don't want to touch all those things. But thing is, that is an amplifier because that unity gain follows in a voltage follows that increases the gain also. Gain is to be 1 and input impedance is increased by the factor RF. And then second stage is a differential amplifier. So I told that the R2, R3 and R1, RF. R2 is not equal to R2 is not equal to R1 and RF is R3 is not equal to RF. Then you have nothing but a weighted sum of difference between the two signals. If you are simply a subtraction, then make it R2 is equal to R1 and R3 is equal to RF. Any doubts till now? This is the basic applications of the operational. You can get it off, no problem. Only thing is always when you study something from the always look in terms of applications. Then only you can realize. Because if you go to the company or interview, if you ask some questions, if you say like this simply and some in circuits and all, they won't accept you. You have to think beyond that what you study. Think means always you have to applications oriented, where you have to learn. Then you get a better placement and a better jobs, positions. Your marks is required until what time? Stepping into the company. Once you are stepping into the company, there is no value for your marks. Always that retention and knowledge. From that perspective, you should study. Then only you can any doubts till that time. Till that time I have discussed only 4 things. One is inverting amplifier, non-inverting amplifier and their applications in a different mode. Normally these instrumentation amplifiers are used in the one is as transducers. Other applications are in most of the biomedical signal applications like ECE measurement, a pulse measurement, even in the brain signal measurement. What is the advantage if you use instrumentation amplifier? This actually I forgot to mention one word: common mode rejection issue. Not only gain of the amplifier increases, it rejects a common signal. That is an advantage of the instrumentation amplifier. But in normal amplifiers, common mode is not rejected. So they use inverting or non-inverting amplifiers. Because in a way that common mode rejected, because normally he knows how that ECG in a movies and all, the electrodes are placed in the 2 arms or 2 legs. Definitely there is a common signal between both the ends, that should be rejected. That's why they use instrumentation amplifiers in the measurement of biomedical. Even that the EEG signals you have seen, no? They kept one call on your head. It includes more than 32 electrodes are there. Under that conditions, any common signals are there that is to be rejected by using an instrumentation. That is an advantage. Why that instrumentation amplifiers are required instead of a simple amplifiers. Even because here this is a resistance transducer is connected across RE and R. Any common signal is between these 2 signals, that is rejected. It only take the difference between the exactly the actual difference between the V and E. that also nullify your offset voltages. Any doubts? Actually, I didn't talk about that basically that slew rate and common mode rejection issue. I'll when I come to that active filters, then I will speak about that slew rate. Here, the common mode rejection. What is the common mode rejection? CMR definition. The common mode rejection ratio means the common mode rejection means if any common signal is rejected. What is the definition formula? Mathematical formulas. What is the ideal value of the common mode rejection ratio? Infinity. What is that formula? That is a gain of the differential gain to the common mode gain. What is a common mode gain? Normally when that input voltage is 0, common mode reject, output voltage are, literally speaking, common mode gain should be 0. Isn't it? But ideally, but practically it is not equal to 0 because of the biasing voltage and all, some voltage existing are some microvolts. Even if you are applying, that is nothing but offset voltage. Therefore, a common mode is to be, in theoretically, you are going to get about 100 dB, 80 to 100 dB. Practically, ideally it is 0. Sorry, ideally it is infinity because AD by 0 is infinity. This point is there. Next, what do you mean by comparator? Okay, let's see that I am using that is that normally comparator is to be used in the operational amplifier as a comparator. Most of the case, simplest is this is a simple example of a zero crossing detector. Actually, in textbooks they use some diodes and all. What do you mean by zero crossing detector? Basically,
when the voltage changes from 0,
not change as 0 means that output voltage changes exactly at 0. Because what is V0? V0 is nothing but difference between V2 minus V1, no? V0 is equal to V2 minus 1. V2 is nothing but a voltage at the non-inverting terminal. V1 is the voltage at the inverting terminal, isn't it? That means whenever that crosses 0, because when it is 0, means negative or positive, isn't it? Means V2 is positive, the greater, then you are going to get positive ECC, as shown in the first slide, no? Beginning of that characteristics. And then V2 minus V1 is negative, that output is negative. That is nothing but the zero crossing. Zero crossing means whenever the input crosses that 0, then output changes its state. Plus to minus and minus to plus. Therefore, nothing. This comparator is nothing but a zero crossing detector. Observe that transition is exactly at 0. This is a comparator circuit with a Smith trigger. Comparator circuit with a feedback. What is the difference you are observed in the previous case and this case?
Positive feedback. Positive feedback.
Positive?
Feedback.
Positive feedback. Next. Just have to recollect that your inverting amplifier, non-inverting amplifier and this circuit. What is the difference?
it's voltage divider. It's a voltage divider.
Voltage divider. Okay. Voltage divider. No, we'll come back to that. In the previous we are shown a comparator. In a zero crossing area, what happens? Whenever that output changes, the output crosses to across the 0, then output changes the level, plus to minus and minus to plus. Now, here also in this case, in a comparator circuit is including the feedback circuit. What happens to this circuit? How it works? If you observe, VA is applying to the inverting terminal, that feedback is connected to non-inverting amplifier. This is a positive feedback. Next is, what happens to that inverting amplifier? In this case, what is the voltage at this point? Voltage at this point is nothing but drop across R1. Are you agree? What is the voltage which is driven by the output voltage V0? Therefore, A voltage at the positive terminal or a inverting non-inverting terminal is nothing but R1 into V0 divided by R1 plus R2. Are you agree? Now, this is a compared. Now, what happens to that VI? VI is compared with respect to the V plus. VI is compared with respect to the V plus. Now, this is a VI minus V0. V0 is positive. This implies what is the voltage? V2 minus V1. What is the voltage? V2, or we can say V plus is equal to R1 V0 by R1 plus R. Now actually what is the differential voltage? Differential voltage is nothing but V plus minus V minus. This is your VI. Are you agree? Now output maintains the voltage V0. No, it's just some voltage. Just some output voltage. Initially that output voltage is at positive saturation. Initially voltage is at positive saturation. Are you agree? Output maintains the saturation voltage of that V plus. Means what is the output voltage now? This is positive. Means this implies that V saturation is positive. What is the output voltage? V plus. This is also positive. Are you agree? V plus is positive. Means this difference voltage is positive. Means VI is less than V plus. This point is clear? VI is equal to V plus minus VI. V plus is positive because V saturation is positive. Means output voltage V0 is a plus saturation voltage. Definitely V plus is also positive. Are you agree? Now, if when VI is increasing until V plus, what is the output voltage? Positive. See that here. Means this is a VI versus V0 your plot. When VI is equal to, okay, is until less than this something called V plus, that output maintains the positive. When VI is greater than that V plus, greater than or equal to V plus, what happens? VI is greater than or equal to V plus. What happens to this? Then that VID becomes negative. According to the characteristics, what happens? Output swings from a positive saturation voltage to the negative saturation voltage. Means if you are further increasing the input voltage, what happens? It will maintain the level of a negative saturation. Therefore, VI is greater than V plus, then that output swings from a positive saturation to a negative saturation. Therefore, this voltage is known as upper threshold voltage. This V plus is nothing but VTHP. UTP. Upper threshold point of the voltage. This point is clear? If you further increases, that output is V. Maintains the level of minus saturation. Now, what is the V now? What is the output voltage now? V plus now. Minus V means V plus is negative. V plus is. If you are further decreasing that input voltage less than this, whenever you going to get this notation, VI is, this is already negative. VI should be greater than this V plus, no? Less than, further smaller than this V plus, then what happens? That output swings from a negative saturation to the positive saturation voltage. Therefore, this is also known as VLTP. Lower threshold point. Means it forms a hysteresis curves. Therefore, this curve is nothing but on hysteresis. Means that output is swings between only two levels. Then what are the advantages of applications of this material? Why do you need it? Because see that you are not doing using any external sources, DC sources. Therefore, both positive saturation voltage and negative saturation voltage are equal, then your UTP and LTP are also equal. Exactly where UTP, LTP is exactly a negative of the UTP, upper threshold voltage. Only thing is, you use identical transistors are used in your operational amplifier if they are working properly. But your experience in laboratory, you never get identical. Positive saturation is about some 10, 12 volts, 11 volts. So negative saturations are going to get 10 volts because of the chain of product. Because not reliable, but the industry standards are there, they are going to get exactly symmetrical. You should remember, don't say that practically you got that in an interview. Normally, sometimes they ask this kind of questions only. Is it identical? Then you recall your laboratory. No, sir. I got V saturation is plus V saturation 11 volts. And this minus V saturation I got 10.5 volts. That may be many reasons. One is component. Second one is a measuring instruments not calibrated. Or many reasons. But thing is, you should be tell confidently they are equal. Therefore, you are going asymmetrical. I want to vary. This way in a symmetrical, this can both are positive or both are negative. It is possible. That by using proper supply voltage. If you use I'll go back to going next slide. What are the applications of that symmetricals? Applications of symmetricals. Why do you need symmetrical? One thing normally in the previous slide you are observed, no? Okay, no problem. Okay. In the comparator, what you are observed? You use the sinusoidal signal, then corresponding square wave. No? Means from that you can conclude a sine wave is converting to the square wave. That is general thing. In general, any irregular signal may be converting into a square wave. Once you are going to get a square wave, from that square wave you can generate any waveform by using differentiator and integrators, whatever you require. Means normally in any signal, when the signal is communicated through a channel, that signal maybe gets distorted due to the many reasons. One is an atmospheric, due to the thermal, due to its component itself, that signal maybe gets distorted, noisy. Means that noisy signal can be definitely converted into a square wave. The one thing. Then advantage applications of the symmetrical. Next is here, I have shown the same thing here. A VTH, we can, by adjusting this V reference voltage, we can keep these two are in the both are positive or both are negative or unsymmetrical. That depends on the requirement. But in the V reference is zero, when reference voltage is zero, definitely you are going to get simple, there is no difference in a zero crossing detector and other things. But instead of zero crossing detector, it detects exactly, that depends on values of R1 and R2, you are going to get identical asymmetrical square waves. But threshold values are non-zero. But in a zero crossing rate, exactly zero. Means I am suggesting you people in your examination, first when you are getting an operational amplifier circuit experiments, first verify the op amp. How do you verify the op amp? Did you verify or simply connected? Simply. When there is an output is not getting, then you blame replace the op amp. In the examination you have only 3 hours, no? Then how do you manage it? You are expecting a teacher to help. Isn't it? Means in any operational amplifier circuits, if you start, you have to verify just simply connecting plus and minus VCC. either you have to ground any one input terminal, connecting in the sinusoidal input to the any one signal, inverting or not. You are going to get a symmetrical square wave, then your operational amplifier is working properly. Even if you have symmetrical, instead of a symmetrical square wave, you are going to get unsymmetrical square wave. On period is not equal to off period, their op amp is not working properly. You should be remember. Before conducting the experiments of any operational amplifier circuits, you should verify. Zero crossing detector, not your voltage follower or nothing. Now in this metric, you are going to get these two are verified by using this V reference. That depends if you are applying a negative reference voltage, both are negative. When that V reference is positive, both the threshold voltages are positive. If you are, depends on that also, you can one positive and lower and negative, then you have to set that reference voltage or choose the proper resistance values R1 and R2. The way in which you design the S metric. This is about the basic application, means what we have discussed till now. Only a negative feedback amplifiers and part of that a positive feedback amplifiers. Any doubts till now? You can ask and try to rectify. Because continuous I speak, no use, no. Unless I try to involving you people. Literally you got some feedback from you people also, that is good to teach. Your answer is partially right, not complete. Filters are nothing but which allows certain band of frequencies and reject all remaining frequencies. That is known as a filter. Based on that responses, we classified filters into 4 categories. Low pass filter, high pass filter, band pass filter and band reject filter. Now, what are the parameters of that filter? Because that filter is a black box. That filter that may be consisting of an operational and some external components. Now, therefore, we can write that gain is to be related by V0 by Vi. See, if you observe here, there is a domain change. No, your input is to be defined in terms of time. But when you are defining that gain is to be written in terms of V0 by S and Vi. Are you aware about what is S? This is a parameter of dash. Use Laplace transforms. Laplace transform. This omega is indicating the frequency for here. Why you are not simply write gain is equal to Vi0 of t by Vi of t? Normally, when you are doing that relation in time domain analysis, that V0 and Vi is to be related by using a convolution integral. I hope this is one of the properties studied in Laplace transforms. Convolution property. Properties of Laplace. Recall. Mathematics. If possible, you can recall, otherwise, the one property is studied convolution. Means if the two signals are convolved in domain, one domain, then multiplication in the frequency domain or the Laplace domain. And remember, recall? Okay. Therefore, based on that, you have defined that is AV is equal to V0 by Vs. And in the frequency domain, what is S? S is nothing but sigma plus j omega. But sigma is very small when compared to omega. Therefore, S is replaced with j omega. Therefore, you got F j omega in frequency domain. That is j omega, V0 of j omega by F j omega. And then this is a complex in nature, therefore which has both magnitude and phase. Now, if you consider the characteristics of the filter, it is a low pass filter. Okay, exactly low pass filter. What happens? It allows that only low frequency signal and reject that frequencies which are above the FP, cutoff frequency. Therefore, this is known as a pass band. Pass band means that signal which allows, okay, that filter which allows the complete input signal, therefore that is known as a pass band, therefore it is also known as a bandwidth of a filter. And rejecting this a stop band region, this is the region from that point at which this is a cutoff frequency, means from this point to this point it reaches almost zero, known as a transition region. Means it not suddenly drops. It takes time to reach to the stop band. Therefore, that region is nothing but transition region. Next one is a stop band region. Means most of the signals were rejected at this moment. Yeah, a partial of that signal is rejected, not completely. This is a low pass filter response. Next slide. These are the characteristics of a different filters. All pass. It allows all frequencies. Sometimes all pass filters are also used in signal processing. Now not analog, a digital. Okay, when you study DSP and all, you are understood. Now in this case, that is the first one is a low pass filter. It allows only a low frequency and rejects the high frequency components. And a high pass filter, it rejects the low frequencies and allows the high frequency. And these two are the band pass and band reject. Band pass filters are normally used in some certain frequencies, band of frequencies. And here they say band reject filters normally used in medical applications. Okay, medical application means they have to reject that because a signal from your human body is to be around 1 microvolt. Definitely that is very immune to that your 50 Hz signal, light or fan. Okay, and to remove that 50 Hz means you have used a notch filter. Now also this is replaced with adaptive filters software. Now these band pass filters are used. I hope if you visit any musical fountains, are you visited? In Matikere is there, in Mysore, that is earlier it was famous. Earlier they played only for music, now they are played for songs also, complete song, lyrics also. Means they use, because why? Reason is a different instruments having different bandwidth. When you compose a song, all are in the same, no. Voice is at 0 to 3.3 kilohertz, a maximum 3.4 kilohertz. From 3.6 to around 6 hertz tabla and all. And from 8 kilohertz to up to 14 kilohertz, that is with respect to the string instruments. Different string instruments are tuned at a different frequency. You are observed, all instruments are, songs are played at the same music? No. Means it depends on that lyrics, they tuned their instruments. Therefore you are going to get a different tones, isn't it? You are observed a same song is to be sung by different people or at different musicians. Definitely you can see the differences. Because that depends on the basics. The similar there, under those conditions, band pass filters are used. One is why I am given this means they are all familiar with you people. If I give something related to something, you are forgotten. Next is the high pass and low pass filter. How do you remember? Easily, you can. This one. Low pass filter is nothing but that keeping those who are studying in the classroom, kick out the other students. Nicely. That is low pass. High pass filter, one who is helping in your examinations. If you kick out the source, then noise is no use. They are also new. That is why you have to remember a low pass filter and the high pass. Now, I am considered simple. This is not an active filter. Is a filters are classified into two categories. One is a passive filters and active filters. Passive filters means that circuits without any active devices. What is the response? What is the difference between the low active filter and the passive filters? Here the response shown here is a response of a active filter, not a low passive filter. What is the effect in the passive filters? Just if you consider this circuit, what is the reactance of a capacitor with respect to frequency? See that? Frequency increases, Xc decreases and Vc decreases. Then what happens is, at the frequency versus V0, if this is V0 is to be taken across the capacitor C in a low pass filter, Then what happens here? Here the frequency increases, that response is to be decreases like this only. There is no constant. It is very difficult to determine the distinguish a band pass and a stop band. Stop band and a pass band. Means at this frequency, the frequency at this is nothing but the cutoff frequency Fc, that is nothing but 1 by 2 pi Rc. Where I am not going to derive anything, just I am trying to transfer a concept of. Means, yeah, this means this is the pass band, this is stop band. You cannot find here a transition. Reason is that voltage across the capacitor goes on decreasing drastically as the frequency increases, because that is non-linear in nature. Now, that is a passive filter. But in case of active filters, when that amplifiers are introduced, then because of that high input impedance, a high common mode rejection ratio and high slew rate, it maintains that a constant voltage, output voltage in the pass band, and decreases after cutoff frequency omega c or cutoff frequency Fc. Until that gain is to be remains constant in case of the active filters. Particularly gain is constant in the pass band, you can say in general, either low pass or high pass or a band pass or a band set. This is about the difference between a low pass and a high pass filter. Means in a low pass filter, output is to be taken across the capacitor C, and in case of high pass filter, output is to be taken across a resistor R. That just interchanging the component values, components C and R. So, next is active, first order active low pass filter. First order active low pass filter means here always normally use this as a non-inverting amplifier mode, and this R1 and RF that we use the gain of the amplifier, that means that is nothing but 1 plus RF by R1 in the pass band only, not in the stop band. This is a gain 1 by RF plus R1 is the gain of the amplifier in the pass band. Now this is the because we use that a capacitor value, this resistance V in, then that voltage at this point is nothing but voltage across the capacitor C. That is given by this expression V1 j omega c by 1 by j omega c, and all. To simplify, you are going to get 1 plus j omega by omega naught or omega c. Because I am taken this value from the internet, therefore it is omega naught. Now we will use that notation omega c, cutoff frequency, 3 dB cutoff frequency. Means this implies that when omega is equal to omega c or omega naught, that magnitude becomes 1 by root 2. That is nothing but a 3 dB cutoff frequency. Why use only 3 dB? This is zero gain. Gain is 1. Why do you use only 3 dB? What is the advantage? 3 dB means what? How do you calculate the decibels? 20 log? V naught by V. Power gain? Gain in power 10 log, because what is the power? P is equal to V naught square by R. When R is equal to 1, P is equal to V naught square, isn't it? Therefore, that gain in power is equal to P is equal to that is gain in dB is equal to 10 log P, not by Pi. In case of the voltages, because P is equal to V naught by V naught square, therefore you are going to get 20 log. Means you are going to get 1 by root 2. Power gain is nothing but half power. 10 log means half power. Therefore, 3 dB bandwidth is nothing but the half power bandwidth. Why you have to choose half power only? Next question was. Why do you choose only 3 dB? You have networks in your subject? You study maximum power?
Yes, sir.
What is that condition?
Input resistance equal to load resistance to get.
Input resistance is equal. If the input is not equal to output, what happens? What is the effect?
We can't drag down most.
Means that power gain is reduced. What is its implication? This implies that at 3 dB, there is impedance matching between the input and the output, source and the input stage. Because of that reason, always we use that 3 dB bandwidth cutoff frequencies. Okay. Are you experiencing that any time ear pain? What is the impedance of the outer ear and inner ear? Same or different? Why? Not inside the body and all. What is the resistance R? R is directly proportional to? No, resistivity.
Area.
Directly proportional, area and inversely proportional to length. Means outer ear resistance is more. What about the inner ear? Less. Still, you are not getting any pain, no? Why? Definitely, the impedances are matched here in your ear. No. Outer ear impedance is more, inner ear impedance is less.
Sir, outer ear is air, sir. Inner ear is fluids.
No. That impedance is matching because I think sometimes you are experiencing that ear pain, no? No. When your throat is blocked. When your throat is blocked, definitely you got, when you even eat or speak, sometimes you are going to get a ear pain. Means there is a opening inside but not a fluid. There is a opening between the inner ear and the throat. There is a connection. That impedance matches the impedance between the outer ear and the inner ear. If that throat blocks, then what happens? That definitely affects your ear. Sometimes you may experience that. Okay, due to cold or something else. Therefore, that 3 dB, this why you have to measure the 3 dB means because of one reason is impedance matching between the source and the input stage and the output stage and the measuring device. And then this is to be when at what rate it decreases. Next question arises. I am not going to derive this. Normally, this is a first order, a low pass filter. Normally, that order of the filter is to be decayed in the transition region that reduces at the decreasing at the rate of minus 20 dB N. N is the order of the filter. In a second order filter, the roll off rate is minus 40 dB. Why? What is the indication of my negative sign here? Negative sign indicating that decreasing slope. Positive sign is indicating that increasing slope. Therefore, here that is to be minus 20 dB. Normally, most of the hardware experiments they use a first order or second order low pass filter. But in this case, the gain of the amplifier can be varied, whatever you require. The first order low pass filter, 1 by RF by R1, you can adjust. The second order a low pass filter. See that why it is called second order filter? You use R2, R3 to R3, C3. Normally use identical stages. Identical stages means R2 is equal to R3 is equal to R and C2 is equal to C3 is equal to C. Okay, this is what is the gain of the amplifier? 1 plus RF by R because non-inverting amplifier. With a non-inverting amplifier, always there should be gain is to be 1 plus RF by R1. What is the gain? In the examination, if they are not specified for a second order low pass filter or high pass filter, you should be assume gain is equal to 1.586. That is fixed. You cannot vary or adjust the gain of the second order filters, Butterworth filters. Don't tell that sir data is missing. You should be remember and then calculate that gain of the second order filter is to be 1.586. So based on that you have to calculate RF and R1 only. And then RC value is to be calculated by using 1 by 2 pi RC. That roll off rate is to be minus 40 dB per decade. Next. The first order high pass and low pass. Then here interchanging the components. R and C values are different. Okay. Then that circuit is to be set. Now, how do you design that filters? You have filter F is equal to 2 pi RC. How many equations are there? one equation. How many unknowns? R and C. F is given. For a given cutoff frequency, you have to calculate. How many unknowns are there? 2. R and C. Which one you are going to assume?
C.
Why? Huh?
R we can change.
Why?
We get potentiometer or
Because there is no variable capacitors are available. A small trim parts are also available. You can adjust that gain or the cutoff frequency by adjusting the resistance R. Therefore, choose always what is the value of that capacitor choosing. That is important. Normally, that is choose the values that to be less than 1 microfarad. 0.1 to 0.1 or 0.01 microfarad capacitors are choose and then calculate the other resistance value. Then that gives the high pass filter. That gain of the amplifier means is to be fixed for 1.586 for the second order filter. For the first order filter, you can set any gain. But only thing is, choose the proper input. It should not goes to the saturation region. Select the gain in such a way that that output should not exceed that a plus or minus VCC. So next, the filters are found. This is a band pass filter example. In a band pass filter, there is a cascade of that high pass with a low pass filter. But only thing is, what exactly you have to choose? Cutoff frequencies are important. For a band pass filter, high pass filter cutoff frequency should be less than a cutoff frequency of the low pass filter. Then only you are going to get a band pass filter. Otherwise, that becomes the wrong suggestion. Therefore, in a low pass filter, order is to be a higher, and then this one, then you are going to get a band pass filter. Then, yeah, that band pass filters are to be broadly classified in 2 categories. One is narrow band and a wide band pass filter. That depends on the quality factor Q. What is Q? Q is nothing but cutoff frequency divided by bandwidth. Means the quality factor is less than 10. Normally that is to be designed for used for a narrow band pass filter. A quality factor is greater than 10. They use it for narrow band pass filters. Okay. Normally that narrow band pass filters and all used in your broadcasting of your television or radio. Next, FM. So next slide. Now, can anybody explain that how this circuit works based on that your previous? Assuming that V0 is equal to 0, then how can you rewrite this circuit? V0 is equal to 0, assuming that. Can you redraw this circuit? Because we have to visualize that, you cannot visualize it directly. Set V0 is equal to 0. Then how this circuit looks? I hope you studied equivalent circuits, no? You have some equivalent circuit. And a MOSFET or transistor, whatever it may be. Now, I am setting that V0 is equal to 0. Source, output. What happens to this? Resistance R. Where is that capacitor connected? 0 means what is its meaning?
ground.
Ground. Means that capacitor is connecting to the ground. C2, R1. This C1 is followed with R2 is also grounded, and then this is grounded. What is this? Circuit.
The first one is low pass filter.
Low pass filter.
Second one is high
Means it is a cascade of
low
low pass. Because if you straight away, if you see that, you cannot assume that. One thing is you have to write an equivalent model, then we can say that R2 and C2 are in a feedback. Okay, R2 is connected, output is taken across the R2 and C2, nothing but. Therefore, this circuit is a cascade of that both C, okay, low pass and high pass, that gives the band reject filter. Because that Q is large, then that bandwidth is very small, greater than 10. Then F naught, you have to determine the center frequency. What is the F naught? Center frequency are not quality factor. Something you have got a notch filter, no? Sorry, band pass filter, your response is like this. This is the F naught, this is FL, this is FH. What is F naught? Square root of FL. What is that? You are linked with mathematics. What kind of harmonic? Geometric mean. Means that's why you should be smart, then you can able to answer those kind of questions. Means that is F naught is nothing but a geometric mean of that high pass and a lower cutoff frequency and upper cutoff frequency FH. That gives you a narrow band pass filter response. So these are band stop filter. Normally see that there is a difference here. When you design a band pass filter, use a cascade. But that same principle is not work out in band reject filters. Then you add the two signals, the first one and second. First stage is nothing but one is a response of a low pass filter and the response of a high pass filter. They are added together to get the band reject filters. But you can do no cascading that. What happens? What is the effect?
We will not get it.
See, in case of the low pass band pass filter, this is the one pass, and then this is the high pass, and then you are adding these two, you are going to get band pass filter, isn't it? But if you are reversing this, are you going to get cascading these two?
So we will already cut off. So we will not get it.
Because already they reached that zero. Definitely you won't pass the high frequency. Therefore, it is not possible to cascade that low pass with an high pass for a design of a band reject filter. Therefore, add summing those two. Means when choosing that values, you should be choose that proper values of the low pass cutoff frequency and high pass cutoff frequency to get the notch filter. This point is clear? Next slide. I taken this circuit from that some website. I draw this and then. Now, band reject filter they use a 20 notch filters. Okay, now this circuit works. Can you tell me directly? Can you once again see that? The common input is applying to that. This is adder circuit only input. There are two. Why it is called 20 network means C R by 2 is a T, one T network, and then R by 2C is the another T network. Means that first one is an high pass filter, the other one is the low pass filter. Add these two and then you are going to get the output with a unity gain on the voltage follower. That's why, because I am not taken any equations, so just refer the book and then how that circuit works means that is to be, if you want you can derive it, that gain and all through finding that voltage at that loads and then you apply, take the differences, so you are going to get this voltage. Because here, how do you design? Because this voltage is V0 and then this is V in, and then you are applying this, so finding this two different sum and then you are going to get this output voltage. In frequency domain, not in the transient analysis. This is about the filters. Okay. Next is we are going to discuss that the how to convert analog to digital and digital to analog. This analog to digital weighted resistance dash is almost identical to dash summing amplifier. Because you are going to give the weightage to the each bit, that's all. I told there is a difference between summer and a summing amplifier and a adder circuit. Adder circuit is simply output is proportional to the sum of the inputs. but summer circuit output is proportional to A into B1 plus B into B2 and so on. You are going to get some weightage to that. In a weighted resistance circuits is nothing but you are going to give the weightage to the each bit. Means you are connecting either 5 volts or a ground using a logical switch. 1 means there is a plus 5 volts, 0 means a 0 volts. Then the resistance R is equal to, we have followed with R, R by 2, R by 2 square, R by 2 cube and so on. In general, for it depends on the nth order filter, nth order bit, that last bit is MSB bit is to be divided by R by 2 to the power of n only. It is a 4 bit. Then what is the expression for this V0? It is an inverting amplifier, no? V0 is equal to minus RF by simply R. There are bits B1, B2, B0, B1, B2, B3. Minus RF by R into B0, minus RF by R by 2 into B1, minus RF by R by 4 into B0. Therefore, finally, if you simplify this, you are going to get, take LCM, RF minus RF by R1 into B0 plus 2B1 plus 4B2 plus 8B3. That depends on the values of this K. RF is equal to 1K and this is 10K. Maximum output voltage is equal to 7.5. What is the resolution then? For this circuit, what is the resolution? Do you know what is the resolution definition? Resolution in the what? A smallest possible voltage which changes with respect to the change in the input signal. When changing the level from 0 to 1, what is the shift? You got? It's nothing but a step size. You can say resolution is nothing but step size. In your laboratory you are done calculate. But the step size is nothing but minus 0.5 volts. Resolution is nothing but a V0 divided by a 2 to the power of n minus 1. A maximum swing we have to calculate, plus or minus 50 volts. This is about the awaited, why it is called awaited resistance circuits. So next. This is R to R DAC. Why it is called R to R DAC? R to R DAC. Because see the resistances are equal to, one they are using R and 2R. Means with respect to any node, if you refer here, node this node or this node or this node or this node, that is symmetrical. On the either side you are going to get 2R only. With respect to this branch, this resistance is 2R. What is the resistance? Because of this virtual ground, what is the resistance here? 2R. What is the resistance up to this point? How do you calculate the Thevenin's equivalent resistance? Setting all bits are 0 except V3. Are you agree? Now when this all are 0, this is grounded. What is the equivalent resistance of these two? R plus R? 2R in parallel with? 2R. R plus R? 2R in parallel with? R. R plus R? 2R. Means with respect to this any node, okay, any node, that equivalent resistance is identical to, equal to 2R only. Therefore, this network is symmetrical. Actually, in some other books, they are not considering this resistance, they are connecting this R here, one more to R here. They are using, if you refer that Rai Chaudhary. Then what is the expression for the V0? Once again, V0 plus 2B1 plus 2B2 plus 2B1 plus 4B2 plus 8B3, V reference by 24 something. Okay. If you use that reference voltage, then output voltage is also a swings between 0 to 7.5 volts. That depends on that reference voltage. What is the V reference voltage you use? Choose here. Logical one means 5 volts. So next. Last one is a successive approximation ADC. In most of the devices, practical device, they use successive approximation ADCs. What is how it converts? See that we have that one is a clock and other terminals is the start of conversion and end of conversion. I hope you studied shift registers. Shift registers. Okay. Now this is the DAC. What are the things either use a R2 or DAC or the weighted DAC. Now we have a comparator. Input comparator is compared with respect to the DAC output. And then when this each clock is enabled manually or automatically. Okay. Once how many bit, for example, if you use a 4-bit DAC, how many bits required? How many clocks are required? Because number of bits plus one start of conversion and other one is the end of conversion. If you choose a start of conversion, now we have some input is applied. For example, 2.3 volts. With respect to the previous circuit, you got that values are minus 0.5, minus 1 up to 7.5 volts. When this comparator is an open loop comparator, when this voltage, because this is a VD minus VA. Initially, when you are using a 4-bit or 8 bits, MSB bit is logically 1 and all other bits are 0. Means preset. All the bits except MSB. Means you have to 0 except that MSB. Means when logic 1 means what is the signal you are going to get? If you have 4-bit signal, 1 0 0 0. Isn't it? 1 0. Where input is something 2.3 volts, for example. 4-bit. What is the equivalent voltage you got? According to the previous circuit, you are going to get minus 4 volts or plus 4 volts. Okay. Now it compares. 4 volts is compared with respect to 2.3, which is greater or smaller? This is smaller. Then what is output voltage? Logical comparator output becomes negative saturation. Nothing but 0. Because we are normally in a comparators or a ADC, they use instead of a 2 sources, they use a single source. Plus saturation VCC and minus saturation is connecting with ground. Means when this VD minus VA is negative, then that what is our comparator output becomes 0. When the comparator become output 0, that implies that reset this bit to 0 and then retime this bit. Set the next to the MSP bit. Therefore, you are going to get 0 1 0 0. What is the equivalent voltage now? 2 volts. Step size I told 0.5. That's why I tried to remember that. 0.5 into 4 is 2 volts. Now it compares. What is the voltage now? 2.3 is greater than 2 volts. Then what happens to this? 1. Means it returns this voltage. Next it compared with next bit. Set to the next bit. Means next bit is to be 0, 1, 1, 0. This is equal to 6. Means that is 3 volts. 3 volts is greater than 2.3 volts. Then that comparator becomes exceeds 0. Therefore, in the next clock cycle, this becomes 0, 1, 0, 1. What is the voltage? 2.5 volts. This 2.3 volts is to be close to the 2.5 volts. That because we have only 4 bits, then this output 2.3 is equivalent to the when the end of conversion bit is enabled. Then it transfers all the signals from a successive approximation register to a latch. It holds the output voltage is equal to 0, 1, 0, 1. In examination also it explains with one simple example. Either a 4-bit or 8-bit. 8-bit means you need to calculate many things. But in a 4-bit you have to verify it and then take it. each clock. Means number of clocks required. This is a successive approximation. Means it until means how many clocks? Until all the bits are verified, that answer, it verify until that all the clock period. 4 plus 2 or n clock pulse plus 2 clock pulse. So next, this is about the successive approximation. Last one is of this topic is a small signal rectifier. What do you mean by small signal rectifiers? What do you mean by a precision rectifiers and the normal rectifiers? Or a precision diode and a normal diode? Are you remember diode characteristics? Okay, what is the, when do you get the output voltage of a diode?
0.6 greater than 0.6.
Greater than
0.6.
0.6. If the input voltage is less than 0.6, what is the output voltage? 0. But in a precision rectifier or a small signal rectifier, even if rectifies or provides the output for input voltage is less than 0.6 volts. How it happens to these circuits? The first one is simply a unity gain follow. There is a voltage follow the diode. When see that when the diode, for example, if you apply some input voltage, what is output voltage? When this see that when this is when the input negative voltage, the positive voltage is applied. Okay, it is positive here. What about the diode condition?
Forward bias.
For diode is it is positive here. It is a voltage follower, no? What is the voltage? When the voltage is positive, what is the output voltage? The first
Output is
positive, no? Then what about the diode condition?
forward.
Reverse.
Reverse one. What is the output voltage?
Output voltage is input voltage.
No, because it is open, no? Diode is the reverse bias when it is open, no? Then what is the output? Is it 0? No. Because when that this junction diode is reverse biased, what is the voltage gain of this amplifier in a open? Because this open means this is open, no? Means in a instead of a voltage follower, that circuit becomes open loop amplifier. Are you agree? When the diode is reverse biased, what is our circuit becomes? Any feedback exists?
No.
No. Means that is open circuit. Means what is the gain of the open loop circuit? Ideally it is infinity, practically it is 2 into 10 to the power of 5. Means when this circuit in the this I am explaining with respect to the first cycle. In the first positive cycle, this diode is reverse biased. Then because of this very high gain, that output voltage will be divided by this gain. Then this diode becomes a precision diode. Means that 0.7 volts is divided by 2 into 10 to the power of 5 or infinity. Means then the diode, what is the diode V gamma becomes 0. Ideally 0, practically it is very small voltage. In the subsequent cycles, in the diode, this is negative. What is the voltage now? And the diode is forward biased, then because there is when the negative is that the practically this diode is reverse biased, and then output is 0. In the next subsequent cycles, this diode conducts and then output is follows the input signal even if that input voltage is less than 0.7 volts for a silicon and 0.3 volts for a germanium. Therefore, this diode is a precision diode. Please understand the difference between the precision diode and the precision normal diode. In a precision diode, the diode V gamma or a diode resistance is to be divided by the voltage gain of the operational amplifier. In the first clock or a first cycle and subsequent cycles it follows. Once this gain is to be this one, then the junction forward bias and then output is follows the input signal. And similarly, for the, see that the explanation is given in this two circuits. Okay, next thing, this is a full wave rectifier. Okay. Then another half wave rectifier, okay, different circuits. Normally this one is used in your practicals. Two diodes. This conducts for a negative cycle. Previous one is when the change in reverse, the diode, then that diode is circuit is working for a positive cycle. Okay, this is for the negative cycle is rectified, and if you are changing the diode directions, then that circuit is working for a positive cycle of input signal. Next lesson. Any questions? I try to cover my best. If any doubts, you can ask me. You stick on to your syllabus and stick on to your exam marks. Marks is also required. I am not telling that you not require much. But if you gain the knowledge, even if your score is just CGPA of 8, that is not a problem. Even if you have a score of 9 plus and then if you don't have knowledge, then no use. Only 4 subjects, 3 hours means most of afternoons, most of the students are free. Make use of the time by doing with your NPTEL courses or something. Don't go with Coursera and all, because when there is no exam, there is nothing you are going to learn. But learn with your NPTEL, then definitely you can. You have to decide, you have to discuss with your professors. Particularly you want to be in a streamline. Nobody can compete with you people except ECE. And learn, because if you have good domain knowledge, you can beat anybody in the technically. That I suggest you people. And take the support of your sirs and all. Going to VLSI, definitely have very good tools. You have to take some NPTEL course related to that things, and then implement, do good project, definitely you are in place in a very good companies. Otherwise you will become a software clerk only. Nothing else, either you go Accenture or TCS or somewhere else. Anybody can do, no? Why do you need engineering degree? One BSc or BBA degree is good enough to manage that things. But why they took engineering degrees, do you know? At least you did a survey of that before joining. Because US and UK people require a 16 years qualification degree course. BCA, BBA requires only 15 years. Therefore, they are not offer them in the companies for the shift into the US and UK. That's why people are coming for engineering. Minimum requirement for the appointment of their things in USA is job requirement is 16 years of education. BCA, BBA, 10 plus 2 plus 3. Then you need one more master's degree is required. Decide, all the best. They have to think, because the problem is I can able to visualize because we have a earlier knowledge. But for the first, for a student, definitely they feel difficulty in reading the Ramakan diacord. With AC and DC amplifiers, it started with that, where that FC comes, what is RF, and there is no explanation for those variables, from where it comes.
Correct.